Welcome back to PC1 for an update on the GT50 development program. So over the course of the last week, we've completed the trial fit of all of the major casings. We've done extensive fitting and measurement of the final GT50 gas generator rotor. That's now off, being balanced, ready to be inserted into the engine. And on Monday or Tuesday next week, we'll be starting the final assembly of the prototype GT50 engine with all of that work now behind us. In the meantime, as I mentioned to you in a previous update, we've been extensively qualifying and working on the fuel system for the prototype GT50 engine. And this is the system that we'll use to map out the entire operational envelope of the engine to get all of the parameters that we need to code into the final flight version of the FADEC. The fuel system that sits behind that, all the valves, all of the protection measures, all of the pumps, all of the hose, all of that hardware, everything down to fuel nozzles, has been calibrated and developed over there on the Rufus One rig and the associated fuel test rig. And then over the course of the last 2 days, we've started doing the combustion testing on this rig here, which we call Rufus 3. And this is essentially 1/4 of GT50's combustion chamber in rig form, 3 fuel injectors and swirlers, and all of the apparatus to control the fuel flow into the engine, the airflow into the engine, and then measure everything that's going on in the combustion process. As we've gone through the GT50 development program, you've probably been watching us for the thick end of 2 years now, working through some of the combustion processes that we need for the engine. And that's because combustion is one of the most difficult things to develop about a gas turbine engine, and there's a number of reasons for that. At this end of the size scale, fuel injection nozzles are actually really difficult to do well, and so we started those really early just to map out exactly what we've got to do to reliably get fuel into the combustion chamber, and then how we could manufacture those and how we could make sure that they don't carbon up and that they're resilient to contamination in the fuels, and that they give us the level of atomization and, importantly, the range of fuel modulation that we need. The engine needs between 10 and 15 times more fuel at max power than it does at initial ignition, and it's very difficult to get that out of it's actually impossible to get that out of a single orifice nozzle without pushing your fuel pump to areas where you're designing gear pumps that can produce those kinds of pressures is really difficult, and designing valves and fuel metering units that can work at those pressures is really difficult. So we've spent a lot of time over the last 18 months or so getting that philosophy right, and then getting the detail of that right, ready for the prototype engine. And then on top of that, the actual process of creating stable, continuous combustion, that's totally different to what you do in a piston engine, where each time you create an explosive mixture, then you give it a spark and it blows up, and then the process repeats. In here, we've got extremely high velocity air that's moving faster than the flame propagation speed of a flame. So if you do nothing, the moment the engine runs, it will blow the fire straight out of the exhaust, and you'll have no fire anymore. So we have to create an aerodynamic environment in the combustor that can sustain continuous combustion inside the chamber in a stable manner, while we're modulating the fuel up and down by a factor of 10, changing the power, operating at different temperature and altitude extremes, and all of those require a very detailed understanding of an area of physics that it's actually really difficult to simulate. You can't really simulate this stuff accurately in CFD, or computational fluid dynamics, which is the aerodynamics design tool, very reliably. So you kind of use the tools to get as far as you can, but then you have to do testing. And so getting to the point where we got combustion working reliably, where we can modulate the fuel the way we need to, where we can control the way we apportion fuel around, apportion air around the combustion chamber, and how we can create stable combustion throughout the operating range, is a really, really big deal. Now, we haven't wanted to play that up, because we obviously don't want to play up any of the really difficult things that we have to cope with. But today, for the very first time, we got the production combustion chamber fired, operating reliably, and we've put all of those risks to bed. So it's not perfectly tuned yet, you wouldn't expect it to be, but it lights perfectly. It lights up in an instant like that, and we can really robustly modulate the flow of fuel and air through the operating range and get nice stable combustion. So what I consider to be the single most difficult thing to do in this engine, we did for the first time today. And so I'm super pleased about that. So I can hand on heart say, when we put that engine together and we run it for the first time, it'll fire and it'll go. And that's how we're ending this week. And then on Monday, we'll start playing around with some of these parameters to get it running really nicely. And I suspect that within a week to 10 working days, we'll have this thing set up so it's got everything ready for that first prototype engine run. So there's a little bit of good news for you on Good News Friday. Have a great weekend, guys.